Hello everyone and welcome back to our WebAssembly tutorial. This is the fourth video. Today we're going to be talking about something a little more involved than the other examples or the last three videos. It's going to be memory. So far we've looked at how to call functions, how to create library functions, and how to stream files. We've learned how to take output from a file or from some WASM files, but we actually haven't really scratched the surface. We've only looked at stuff where you can modify primitive values, so integers and that sort of stuff, and you can just pass those around, but we haven't actually dealt with any of the memory. And that's where WebAssembly really shines in terms of its advantages over using pure JavaScript. So with JavaScript, you can run all sorts of things, and it's an amazing language. But WebAssembly is a lower level language that communicates with the CPU at a lower level than JavaScript does. It still has to obey all the rules of JavaScript, such as file access, but it's just a much faster language. And especially if you want to do big data parsing or graphics and graphic intensive stuff, that's going to be on the CPU, which is where you're going to be using pointers, because if you're going to be passing in a massive array, you need to pass in a pointer and a size. And we really haven't learned how to actually send in an array of anything for that matter. And that's what we're looking at today. So I'm just going to draw a diagram of what memory looks like. And you can pretty much think about memory as an array, and it continues on forever. Not forever, but you get the point. And this is something that you'll see in computer science classes and whatever computer classes in general. And this is just how memory is stored in arrays, and each cell has an index or an address all the way up to big N minus 1. And WebAssembly is no different. We're going to be interfacing with a sandbox memory that WebAssembly provides that we get with the browser, and this memory is what our programs that we write in C will communicate with. So when we allocate a pointer, so if we say, for example, integer pointer, or sorry, we'll say character pointer, a string is equal to null. I mean, technically you wouldn't think that this would point to anything, but it points to 0. So that points there. So if we want to write to memory, it's just going to be the same thing as if we were writing to memory in C. So when we say mem set or mem copy, when we set a string and say this is equal to, I don't know, hello world, or I'll just say hello for now, what we're going to get is that it's going to either find some memory or find space for 5 characters, or 6 rather, because it needs a terminator. But so let's just say it found index 1 as its memory, and then it'll just set the bytes there. Now that we know how to do that. That's with C. That's just using malloc and all that, and we'll talk about what we need to do for malloc. But how do we actually pass memory in with JavaScript? And it's going to be the same, or it's going to be very similar. There's not going to be any automatic function that we can just call malloc in JavaScript, but we'll look at that later on in this video on actually how we can in fact call malloc. But the principle is the same. You're going to take some buffer, and this buffer will point to the sandbox memory. So let's just say our buffer is here. This is essentially an interface to the sandbox memory that the browser provides us. And you can write to it and do whatever. You can modify it. You're not going to have any segmentation faults unless you go over what the configured buffer size is. But it doesn't matter. It's what we're going to see is that it treats it exactly like an array. So we're going to be able to write to it like an array, and we're going to be able to pass in arrays and decode and encode arrays, and it's going to be very cool. So we're going to take a look at a couple examples today. We'll actually write a little bit of a library. I don't know if we can call it a library, but it's on the way to a library. So let's go ahead and open up our WebAssembly folder. I have a couple of files open. So we're going to start with just memory. And I'm going to create memory.c. This is going to be where we're running stuff. And what we will do is we are going to include mscripten.h, and that's all we're going to need. We're going to have our main function, which just returns 0. And this is required for all libraries just because we need an entry point, or all WASM files because it's an assembly file. You need an entry point. We're going to have mscripten keep alive. So we're going to define one function now that takes in an array. So a good example is to say, all right, we'll take in an integer array and sum up all the elements. So it'll return an integer, and we're going to just call it accumulate. And we're going to be passing in an array. We might not know what the size is, so therefore we have to pass in a pointer. So we're going to say integer pointer array, and then we pass in the size as well. So there are two arguments here. The pointer, which is whatever this might be. So if it's an array of characters, it'll point to some address, but we're going to pass that in as an argument, just as a number, because a pointer is just a primitive value. It's just 32 bits, and you would pass it in like as if we were streaming. So with streaming, we passed an n here, and we took exports.sum of n integers, and we just passed in the value, and it's going to be the exact same. We're going to pass in the address to the first value. So we have the integer pointer array and integer n, and then we're just going to calculate a sum, so is equal to 0, and then we're just going to sum up all the elements. So while n sum plus equals array at minus minus n, just a quick way to do that, and then return sum. So this loop will run while the counter, which we're just going to, because since we're just summing and the order doesn't matter, we'll just start from the back. But while n has some value, or is greater than 0, then we want to take that element, the previous element, or the element before the index. So this just computes the sum. It's that simple. And what we can do is, let's go into memory.html now. So we're in our HTML file, and let's actually go ahead and compile this. So I'm going to open up my terminal, and I need to find command prompt. I'm going to zoom in for you guys, and we'll go cd //source /web, nope, not that, tutorial, and then we're gonna say cd memory, and then we have to activate emsdk. It's just like that. You'll get a couple things, and then we're gonna say emcc, and our file is called memory.c. So memory.c-o, and then memory.wasm or .js, sorry, because we output to a JavaScript file, but we don't actually use it, but it's just for the exports. I haven't found a workaround to that because I don't like outputting to a JavaScript file, but we don't actually need it. It's just there because we need the exports to be configured in the WASM file. And we'll probably end up doing a deep dive, one stream or a longer video perhaps, when I have some more time, and we'll actually look at a WASM file and the structure. But for now, we just want to get the basics through, and then we'll actually start looking at projects and more advanced stuff. So we're going to do our streaming the exact same way. We're going to be working with streams from now on. So we're going to have variable exports just to store globally in our JavaScript. So exports, and then we're going to do the streaming. So WebAssembly dot instantiate streaming. We're going to fetch memory.wasm. I can actually close that there. So this, and then our we will have an empty body for now, but that's going to change later. So we have empty for now, and then we say .then results exports is equal to results.instance.exports. I still have the button from last time, which just is a trigger. So all we have to say is, well, you have to create this function, run wasm, no arguments. And how are we going to do this? So we need to take in a pointer or an array and the size. So I suppose we can start by just creating an array. So I'll say variable array is equal to new uint32 array. And we'll just say it like that. And then we'll say for variable I is equal to 0, I is less than 10, I plus plus. And then array at I is equal to I times 2, we'll say. And, well, okay, that's all good. We have an array. And now let's go and call our function. So we'll say variable sum is equal to exports dot accumulate. And now we're stuck. What do we use as the address? Again, this isn't configured with our interface. This is just an array in JavaScript. I don't even know if this is proper. I don't even think this is a proper way to declare an array that you can write to. But we're going to pass in some value and then 10. And then we will just say document.query selector hashtag ret inner HTML plus equals, just like so. All right. So a couple missing pieces here. We have the output, but we still need this little pointer here. What are we going to say for that? And lucky for us, this little object here, that's the environment object, and we're going to be able to pass stuff in through there. And this is going to be where we get to initialize our memory and then interface through it. So we have to first set up our memory block. And we're going to say variable memory is equal to new WebAssembly dot memory. And we have to pass in a descriptor here. And the descriptor just sets up the size. So we're going to say initial. Initial is the initial size of the memory, and then maximum is just how far it can grow. So we'll say 256 and it can grow to 512. And these blocks are fixed size, I believe 64 kilobytes. Someone can fact check me on that. But this is our memory object. And now we need to pass this in to here. So this is our environment object, and we're going to just specify that with JavaScript. So we're passing in JS memory, and mem is just memory. So that's what we have here. And this is just how you specify a memory object for WebAssembly. However, we're not done just yet. This could work and all, but we aren't able to get our result yet. And the reason why is because once we actually instantiate streaming and are successful in that, we need to update our pointer to memory, because this just gives us, this allocates the space for the memory, but this pointer might get updated at some point when we're streaming. So we need to, in fact, say memory is equal to results.instance.exports.memory. So we're just updating our pointer here. And now what we can do is we can use this memory object in our function and just index into it using the array. So with the array, we can initialize the array using a buffer. So we're just going to say memory.buffer. And this just gives us the array buffer corresponding to the memory. And this integer, this little structure here, this is simply a pointer to that. And then what we're doing by accessing this is we're just getting the ith element. So array at 0 is equal to I times 2, 0 times 2 is 0, and so on and so forth. But we still need to figure out what we're going to pass in as this pointer. Now, if you look at the constructor here, we just pass in the buffer, and this is looking at the 0th element in the buffer. And like I said, we're not worrying about any segmentation faults, stuff like that, because we're not dealing with malloc just yet. But exports.accumulate, we can just pass in 0 as the address because the first element starts at 0. And we're taking the pointer to the whole buffer here. So this should be good. I am led to believe it should be good. So we have our buffer, we point to it with an array, and then we access it and set elements. And then this buffer, again, is what we got from the streaming. So we're updating the memory that our C program can access, or the WASM file can access. And then we call the function, the exported function, with the pointer to the array, and then 10 for the number of elements. And let's go ahead and run this. So I have the server set up here in Visual Studio Code. Results.instance, I misspelled. There we go. All right, so if I hit trigger, we'll get 90. And that's just the sum of, it's 0 plus 2 plus 4 plus 6 plus 8 plus 10 plus 12 all the way up to 18. So we get 90, which is a good sum there. And yeah, so that is a way to pass in memory. Now let's try and take memory from a C program. All right, so we can head back into our memory file, into the C program file, and we're going to create another function here with the same tag mscriptin keep alive. And this time we're going to return some memory. So we're going to return an array, and why not return a string, something that we can actually visibly see. So const char star get string, and we will just return hello world. So what this will do is we're going to take some memory, and this is determined with malloc, actually, or not malloc, but this is determined by the runtime. And in the C program, or the WASM program that this gets compiled into, will actually just allocate some memory. It'll allocate at some point, we'll call this P, the value P, and it just allocates all the way over to the 0 value, which is going to be P plus 13 or something, I believe. But it's going to find this value P, and it'll allocate the string, and it'll set the values there. And then what just happens is it returns P, just the value P, and that's all this is. Again, a pointer is just a primitive value. And now I guess we'll go ahead and recompile again. And now our WASM file has that actually. What we can do in memory.html is we'll create a new button, we'll say. And we'll say button on click is equal to get string. Oops. And we'll try and copy it. Copy string. So then we're going to create this corresponding JavaScript function. We'll say function like that. And let's just go ahead and call it just call the function like we would. So it's going to be exports.getString, or getString like this. And this is going to return an integer value, and we're going to and it's going to be an offset, so a pointer. And the same way that we're going to be able to index into the buffer to write memory, we can also index to the buffer to take memory. So instead of allocating a uint32 array for 4-byte integers, let's allocate a uint8 array. So we're going to say variable string, or we'll say string memory, or actually, let's say bytes, is equal to new uint8 array, and we're going to initialize it at memory.buffer, so with that array buffer, and then we will offset it not by 0 this time, but by the pointer, because the pointer value, which is just P here. So now this array here points to the first character, it points to the H, and we can print it out actually. We could, but we need to decode it first. So we're going to say variable string is equal to new text decoder UTF-8. So we're just going to decode it as that dot decode, and then we're going to say memory or bytes. I'll do this on a new line so it's more readable. Bytes dot slice, and we're going to slice from 0, and end will be 13 or 14. I'm going to say 13. And then all we just have to do is console.log string, and then we'll also copy it. So we can, then a cool JavaScript command for that is navigator dot clipboard dot write text string. This will work. I believe 13 is the string length. We're going to actually programmatically determine that, but let's just make sure that this works here. So we've compiled memory.c to wasm, and let's go ahead and reload here. No console errors so far. If I copy the string, we get hello world, just like that, which is perfect. And if I hit Command V, scam warning. Oh, I don't know what that is, but you can see that we can paste it around. So copy, I guess JavaScript, or the browser doesn't like that JavaScript put something in the clipboard. But we have the hello world string, and I'll prove to you that it works and it's not just some hoax. Let's say, let's do hello wasm. We have to recompile. I'm gonna reload, copy string, hello wasm, and we have some extra character here, but that still works. Now this extra character is because the new string is a little shorter. So let's go ahead and programmatically determine where that terminator character is. And again, since we're working with memory written to by C, we're going to find the 0 as that terminator character. This might be P plus 14, but we just need to look for a 0, and then we will know where the end of the string is. So what we can do is we can create a string length here. So variable is equal to 0, and then a quick way to do this is while bytes at string length does not equal 0, string length plus plus. So we just keep incrementing until we find a 0. And then when we say slice, we just want to slice to string length. And then I'll go ahead and reload, copy string, hello wasm. And we can do that. And need to recompile. We get the whole string, not just part of it, but the whole entire thing up until the terminator character, which is super cool. Now, you might be thinking, well, okay, wonderful. This is actually very cool. But there's a lot of stuff of why do we want to actually just interface this every time? Can we kind of automate encoding and decoding stuff? And also, what about memory accesses? Because what if our program wrote to address 0 and we're now overwriting it? A good way to kind of prevent this without writing too much JavaScript protection stuff and using built-in functions is just to call malloc. So I'm going to leave memory as is, just because this works, and I'll leave that there in the commit. We're going to start with a new file, malloc.html or malloc.c. We are going to create a function. So we're still going to do, we're still going to do include mscriptin.h, and then we're going to have our entry point. And then let's have the same function as before, or the same set of functions. So I'll just actually copy this. So we have getString accumulate, and we have our main function. But let's allow ourselves to actually allocate memory. And a good way to do that is just going to be, let's call malloc in a C function that then gets compiled into wasm. Because once again, we don't want to have to force ourselves to do that with just the buffer. That would be a mess, and there would be so much code going into that when we can simply just call malloc, especially because you can call standard library files in C. So we're going to include standardlib.h. Okay. And then we're going to have mscriptin keep alive. And it's going to be, we're going to have a malloc function. So it'll return a void pointer, wasm malloc, and integer n. And then we just return malloc, and we'll pass this in as a size t. And we just return malloc n, like so. And then because we're calling malloc, you have to call free as well. So we're going to create another function with the mscriptin keep alive tag. And this returns void, and it's called wasm free. and we pass in a void pointer. And this time we're just going to call free pointer. So malloc and free deal with this memory. But again, all the stuff that C already knows how to do is just done using this new sandbox. And we don't need to worry about calculating any of that. It's taken care of by malloc. And now what we can do is we can compile. This time we have a new C file, so emcc malloc.c, and we'll compile it to malloc.js. And if you go into Visual Studio Code, you see malloc.js is there. And also malloc.wasm. So let's go into our malloc.html file now. And I'm going to copy everything from memory.html. So I'll just actually copy and paste in. And we can just go ahead and let's try and run this. So let's go to malloc.html in the server. All right, and I'm gonna hit trigger, still works, copy string still works. Perfect. Okay. Now, oh, actually, we need to update our streaming. So the memory is still gonna be the exact same, but this time we're gonna instantiate streaming with malloc.wasm. So that's the one change here. I'm gonna hit save, and we reload our file, and we see that there's an error. Import object field env is not an object. Okay, so what it's referring to right now is this. So this is our import object where we sent in the memory. It's trying to find something called env. So let's try just passing in env as an empty object and see if that helps anything. All right, import object field mscript and resize heap is not a function. Okay, so what is this? Well, this is going to be a callback. It wants a callback. But why does it need it? Well, we're calling malloc here, and malloc may need to find memory that isn't available, so it might ask to resize the heap. In which case, if you look at the wasm file, it's going to malloc gets translated to a function that may need to resize the heap. So if you go into the wat reveal in file explorer, and I'm going to drop in the malloc.wasm file. If you can see here, it's trying to import something called import env mscript and resize heap. And this is just some function that it's going to want to call when it calls malloc. So we have accumulate here, and then we also want to find wasm malloc, if it can find that. Here we go. This is what it was. This is what I'm looking for. So wasm malloc. I suppose I don't know what any of this means because I haven't actually looked into the format of this. But what I can hazard a guess that this is some address and it's trying to call the import function. So we needed to actually define it for wasm, and this is something that you can do. You can pass in functions and callbacks so that C functions can call JavaScript functions, which is quite cool. And we will definitely end up looking at that at some point. But we need to define this callback, so it's going to be in the environment object, and we're going to call it mscriptin resize heap, and it's going to be a callback. So we call in pass in function, and it's going to take in an object or a number called delta. And lucky for us, this memory object has a function called memory.grow. So we just call memory.grow delta. So we just route this callback, this resize heap callback, to increase the memory pointer that we provided, which is quite awesome. But now this memory pointer once this is all loaded, the memory pointer will be updated to point to the sandbox memory. So let's go ahead and reload this now, and we don't get any more errors, which is wonderful. Okay, so let's try and use our malloc functions. So we don't necessarily want to, again, we don't necessarily want to set memory at 0. We might just want to do it anywhere. So what we're going to say is, we're gonna say, variable pointer is equal to exports.wasm malloc, and the size is going to be 4 times 10 because it's 4 bytes per integer and 10 integers. And then we're going to say the array is a new integer array pointing to the buffer, but this time we're going to offset it by the pointer. All right, and then we're going to set that there. And then this time when we call exports.accumulate, instead of passing in 0, we're going to pass in pointer. And then afterwards, we're going to call exports.wasm free pointer. It's just so we clean up our memory. Let's go ahead and reload this. And we're going to do the trigger function because that's what actually calls this. So trigger, and we get 90, which is beautiful. And it's still working. And I can actually go ahead and print out the pointer or console.log it just so we can see what we're actually getting. It might end up being 0. Oh no, actually, it's giving us 5244, whatever that number is, not 0. So it's allocating memory where it finds it, which is great. So there's no memory conflicts, and we just let C do all of it. We let all the overhead go to memory.grow and the built-in function malloc. This is a good way to do it. I like this a lot. But there are a couple ways that we can create a couple functions to help us out here. So we have our malloc and we have our free, but stuff like this, decoding and then also encoding, can be a bit cumbersome. I don't want to do that over here. I don't want to have to write this loop every time we want to call a function that takes in an array. I want to delegate that to some other function. So we're going to have a couple of functions here. We're going to start with an encoding function. So we're going to translate memory from JavaScript and we're going to pass it to the buffer. So we're going to say function encode array. We're going to pass in the array object, the length, and the size of, which is default to 1. So this is just the number of bytes per element in the array. So we're going to have our pointer, we're going to have our output, and we're just going to do a little if-else on the size. So if size of is equal to 8, then we have an 8-byte element, which is just going to be, we're just going to be dealing with integers right now. We won't worry about anything more complex like floats or doubles. We're going to be dealing with unsigned integers, which represents characters too, so strings. So if the size of is 8, then we say pointer is equal to exports.wasm malloc length times 8, and then output is equal to new big uint64 array memory.buffer pointer. So what we're saying here is, all right, the output, we want that to point to the buffer, offset by the pointer, and this offset is in bytes no matter what the size, but we want to write it in 64-bit increments. And then we'll do else if size of is equal to 4, and then pointer is equal to exports.wasm malloc length times 4, output is equal to new big, or sorry, just uint32 array memory.buffer and pointer. And then we'll do one last one, else if, or just we'll say else, and we'll just default it to 1. So pointer is equal to exports.wasm malloc length, and then output is equal to new uint8 array memory.buffer and pointer. So again, pointer is always going to be in bytes no matter what, and we're interfacing into the array buffer that the sandbox is at, and we're just offsetting it by the pointer that we get. All right, and then let's go ahead and copy our elements into it. So we'll say for variable I is equal to 0, I is less than length I++, then out at I, so the output array is equal to array at I. And then we return pointer. So we've written to the memory that we have allocated using malloc, and then we want a return pointer here, just so we know where we are with it. And what we can do now is we can call this function encode array in run WASM with a predefined array. So we will have our array being is equal to, and I'll just say 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, and I'll do 20 just so we can do a proof of concept and just play around with the size. So that's our array. And then we're going to say variable pointer is equal to encode array. And we're going to pass in the array pointer. The length is going to be 10 elements we'll start with, and then the size of is going to be 4 because we're doing integers. And then we can actually just get rid of all of this stuff here. So we don't need to do a loop. We can just get the pointer, and then we pass that pointer into accumulate, and then free it afterwards. So I'm going to reload, trigger, and we're still getting 90. Let's try increasing the length to 11. 110, because we have that extra 20 out in the back. Awesome. Let's try a decode array, but I essentially just want to replace what this is. I also want to replace this loop so we don't have to call it every time. So we're going to have a couple of functions here. We'll start with decode array, which just takes in a pointer and a length. And we're just going to return it as a byte array. So return new uint8 array, memory.buffer. And we're just going to call slice on it, just like we did with this string. So the array.slice from pointer to pointer plus length. So we're going to get length number of elements. And then if we want to do it as a string, so function decode string with pointer and length, then we're just going to say return new text decoder utf8 dot decode, and then our argument here, the input bytes, is just going to be decode array with pointer and length. So this is decoding a string with a fixed length, where we know what the length is. Now let's try doing it where we don't know the length, so we just have a pointer. So in our example of when we just return whatever the string is, so function decode string pointer. So we're first going to get the memory. So variable bytes is equal to new uint8 array, memory.buffer, and pointer. And then we're just going to do the counting again. So variable string length is equal to 0. And then while memory at string length does not equal 0, string length plus plus. And then we're just going to return the text decoder again. So return new text decoder utf8 dot decode memory. So we're now sorry, this should be bytes at string length. So this time we're interfacing into this array here. So we're going to call bytes.slice, and since we're already offset by the pointer, we just need to do 0 to string length, just like so. All right, and let's call this decode string function up top when we actually need it. So we have pointer is exports.getArray or getString, and we can just replace all of this with variable string is equal to decode string exports.getString, just like so. So we call the function, we get the pointer as the const character pointer, and then we just decode it without knowing the length. So let's go ahead and just recompile to make sure that we're all good on that front. I'm going to reload here. Trigger, we still get 110. Copy a string gives us this. And I can still paste it and do whatever I want with it. And that's memory, or at least an introduction to it. We're going to be doing a lot more with this, but in the time being, this is a good introduction, and we're going to soon be looking at importing JavaScript functions, just like we looked at with the resize heap. And we'll also be looking towards a project and some more explorations with WASM, maybe how to write your own WASM if you wanted to, if you were that crazy. But you know, maybe we'll end up doing that. Yeah, so that is memory in a nutshell. hope you guys learned something. And this will probably be the last WebAssembly video until I get back. So I'm leaving you guys with a couple of introductory videos, and then we'll start looking at a project at some point once I get back in August. Yeah, that's pretty much it. Hope you guys enjoyed, and I will see you guys next time. Have a good one.